looking at velocity distributions, just a quick look at it. It's an interesting fact. And looking at phase changes, that gets a little way more relevant to what we're doing. So what I'm showing you here is known as the Maxwell-Boltzmann velocity distribution. And it basically, as a function of temperature, it tells you what the probability of finding a particular velocity of a molecule in a gas is, because they're not all going to be at the same velocity. It's going to be all randomized, but there will be one velocity that is most probable, and then there will be some that are much greater than that and some that are less than that. And that's what this distribution shows us. So this is a generic sort of plot of this distribution. A distribution function, again, tells you the probability of finding a molecule at a given velocity. So it's a function as a function of velocity. And so, I mean, you might have had some experience with type of continuous distribution functions here. The total, for example, the total number of particles in your sample. Let's say molecules to be specific. That would be n, that would have to be an integral over this thing to infinity. From 0 to infinity of just your distribution function dv. And so take a look at this distribution function. Of course, it's a function of velocity. It goes like v squared, but it also goes like e to the minus v squared. So at low values of v, it is like v squared, so it increases. But then at higher values of v, the e to the minus v squared term kind of kicks in and causes it to exponentially decay as v gets very big. It sort of dominates this part. You'll also notice it's a function of temperature, inversely related to temperature in many ways. At first, it's like, it goes like, well, this is not being plotted as a function of temperature, but you'll see that it does matter. But I just wanted to sort of remind you that with a distribution function like this, if you knew your temperature and you knew the mass of your molecules, you could then do some calculations about that. Like, for example, find the average velocity, or average speed would be a little more appropriate. And in this case, v average, well, you have to integrate over your distribution function, but it has to be multiplied by the velocity, by v itself. V times f of v, this whole big mess, dv, will give you your average velocity. And that's sort of what we do with these type of continuous distribution functions. Also, you could do the same thing for the average of the v squared value. Regardless of that, this is all just interesting that I just wanted to point out without doing any crazy work on. But, oops, there we are. Now, as the temperature increases, this curve gets flatter. And of course, the maximum and at most probable speed, the peak, goes to higher values of speed, but it's not in any super obvious way. But this is what comes out when you apply a statistical formulation to these big systems, which is totally appropriate and totally accurate. So just very interesting how your distribution function spreads out. Of course, at this higher temperature T3, the tail of the exponential curve goes on for a while, but they just didn't really want to show it. But this is the statistical nature of a gas. I just wanted to point that out because it is in the chapter, but I don't want to you to have to do any particular problems with it. Just to know something about it. Phases of matter is a different thing. This is really important. And what we see here is a pressure-temperature phase diagram. Let's do blue. And what the phase diagram tells us, it gives the phase, or it shows the phase, liquid, solid, or gas, gives phase and boundaries for particular pressure, temperature values. And so this is of a typical substance. This is of, as an example of a usual substance that expands upon heating. Things would look interesting if it contracts on heating, and there are some. And so what do we have here? We have a couple things to see. They show you in the upper left, this is the solid area. The bottom rightish is all vapor area. And then at some point here, we see in the upper right boundaries for the liquid area. All along these curves are pressure temperature variables at which phase coexistence occurs. So let's point out a couple things. Each boundary has PT values where phase transitions are occurring. And at that pressure and temperature value, you might either be melting your solid into a liquid, right? But usually in your process, your temperature stays constant until all of your material, but like a phase coexistence is occurring at that point. Right, so it's the coexistence, CO, coexistence of two or more phases. We'll just say phases. Good enough. Recall the fusion curve. Up top there. So it separates your solid and liquid. All PT points on that curve are a solid liquid phase equilibrium. Equilibrium, E-Q-U-I-L. You have your vaporization curve. And basically the same idea. Separates liquid and vapor. And all points on that curve, pressure, temperature points, all states of a solid, liquid, or gaseous or coexisting system, all of those pressure, temperature points are in a liquid-vapor phase equilibrium. And last is your sublimation curve. Sublimation curve, that's pretty ugly, I apologize. right? So that separates solid and vapor. Not usually seen. I mean, we don't usually experience that. With, of course, carbon dioxide ice, solid carbon dioxide, easily sublimates, and so you see it turning immediately into a vapor. It doesn't do well as a liquid at particular temperature, room temperature, and atmospheric pressure. And so all pressure temperature points on the sublimation curve are a solid vapor phase equilibrium. And you'll see they usually occur at fairly low pressures, right? So like on Mars and stuff, water pretty much just probably, from ice, probably often sublimates right into water vapor. And certainly carbon dioxide does as well at these very low pressures. There is a triple point, and I'll add that in here. Triple point. Ooh, it's not having a good time here. T-R-I-P-L-E, triple point. And you can see it's called the triple point on the diagram because the three curves intersect at that point. Here, this is one PT value where solid, liquid, and gas coexist. Vapor, let's be accurate. And it's a property of the substance itself. So often when you look at properties of substances, when you look them up, they'll give you the triple point. The triple point of water is this value that everybody could sort of agree with and experiment and determine, etc. What's interesting is this critical point that you see out there, because the vaporization curve just stops. And it doesn't just stop because they decided not to draw it. It stops because there is no more PT points at temperatures greater than TC or pressures greater than PC at which you have the coexistence of the two. It is a strange thing. So let's quickly just sort of take a little trip, literally. What do you mean? Well, let's look at curve A, or trajectory A. T equals 0. Trajectory A. T equals 0. Right? You start at some PA value. Trajectory A at constant pressure, we're going to increase the temperature. T equals 0, solid. Okay, keep increasing the temperature. Keep increasing the temperature. The solid gets warmer and warmer and warmer until it gets to this point right here. And then what happens? At that temperature, it starts to melt. And essentially, you have to add heat energy to increase the temperatures of things. You keep adding heat energy here, the temperature doesn't change because you have the coexistence, right? Coexistence of solid and liquid. And until all of the solid is melted into a liquid, and then you increase your temperature more because you're all liquid. And then you intersect the vaporization curve. And at that point, adding more heat energy causes you to make vapor and have the coexistence of liquid vapor. until eventually you have all vapor. Then you can keep increasing the temperature out and out. You can see here, P sub S, right? So T equals 0, solid, melts, that's what it's supposed to say, melts, and then vaporizes. If we look at trajectory S, at constant P sub S, T equals 0, solid, right? But eventually you get to this point T sub D, T equals T sub D, and you get sublimation, a phase transition, solid to vapor. So you have the coexistence of the solid and the vapor until eventually enough heat energy is added and there's no more solid, it's all vapor, and then it just keeps going, increasing its temperature. You can play the same game and go along trajectory D, starting at 0 pressure. You have all vapor. You're keeping your temperature constant. You increase the pressure. The vapor can condense immediately to a solid at T sub D. If you're above that triple point temperature and you do the same type of thing, your vapor can then condense into a liquid, and then up here at higher and higher pressures condense into a solid. We're not familiar, we don't experience day-to-day increasing pressures to change the states of matter, but it happens. It's usually temperatures, right? So that's the example. Up here, above this critical point, things are weird. And essentially, if your temperature is greater than the critical point temperature here, and you want to take a horizontal trajectory increasing the pressure, there is no distinction between vapor and liquid. There is no heat of vaporization needed to be added such that it vaporizes or taken away such that it condenses. It's a very strange thing above this critical point. And so it's just very important that we stress that at or above P sub C and T sub C, no distinction. Between liquid and gas. I mean, your temperatures are so very high or your pressures are so very high, or both. And what's important is that there's no phase transition, right? We can measure this stuff very carefully. And, you know, ordinarily you take your solid and you start adding heat energy, and all of a sudden it stops changing its temperature because you're having to add heat of fusion, right? Heat of fusion eventually to change the phase of matter, but the temperature doesn't change. So you can see that. You can see that, and you can do the same game up here, but experiment shows that there is no phase change. It just keeps increasing its pressure, or going this way above out here keeps increasing temperature. So if you kind of did one of these, did a trajectory like this, out here you wouldn't see any stop in temperature change and change in some phase. It's very weird. Don't know how to explain it. Good enough. Let's move on. You notice we were doing a pressure-temperature diagram. That's a nice way of looking at the different phases of matter, right? But you can also have a pressure volume diagram, right? The PV diagrams are what we usually do. And so I'm showing you the PV diagram of a fairly realistic material, one that will condense, so like a van der Waals gas, not an ideal gas. In ideal gas, the isotherms are always just hyperbolas and nothing happens, but here we have problems. So you can see the isotherms at the high temperatures. As you get to lower temperatures, how the pressure and volumes relate for this material, and you start getting this little kink in your PV trajectory. At some point here, you've hit the critical point, and that's this critical point. It's just hard to see it because it's a pressure volume diagram. Below that critical point, so actually I shouldn't have started up here, because up here is in this region. I should really have started low and say at low temperatures, you take a vapor, you compress it. At some point, it starts condensing into a liquid without any pressure change, and then it's all liquid, and you can increase the pressure and decrease the volume. But it's really sort of hard to see here. So if we put them all together, this is what you would get. You'd get a surface that represents all possible pressure, volume, and temperature values, a particular state of the system. And this is your complicated surface. If you look at its projection in the pressure temperature regime, you'll see that particular kind of phase diagram as we had. If you look at it in the pressure volume regime, PV, you get something more complicated. So PT is nicer to look at for phases. It just is. But they're all part of one three-dimensional surface that this generic substance has to obey. That its pressure, volume, and temperature triplets must always be somewhere on this surface. It's complicated, but start wrapping your head around it a little bit. This is a little bit different. This is an ideal gas. And we're not looking at phase changes or anything. We're just looking at a pressure, volume, temperature, ideal gas surface. And so this surface, P, V, and T, must satisfy PV equals nRT. So you can see in PV diagram, here are your isotherms. Okay, well, where are they on a PT diagram? Well, lines of constant temperature on a PT diagram are vertical lines, right? So if you project this onto your three-dimensional curve, your PVT surface, this is what they look like. This is what your isotherms look like. Here on a PT surface, here are your isotherms. What are your isobars? Well, your isobars are lines of constant pressure here. Well, they sort of go along this way. Lines of constant pressure, and along this way. Last would be lines of constant volume. Lines of constant volume on this diagram are vertical lines, right? On this diagram, they're these angled lines. So very interesting, but this surface should represent your your ideal gas law, essentially.